Typically, moving human joints requires minimum effort and minimum work. Thus, to be consistent with human physiology, a joint model should require minimum work to move. This implies also minimum ligament and cartilage deformation. This behavior is in fact assumed in musculoskeletal multibody models, which do not consider the contribution of joint deformation work in the equilibrium of the joint itself, which is balanced just by the action of the muscles. However, this hypothesis is normally not verified. So we ask ourselves whether different models respect this hypothesis, and in the case, what will be the impact of violating this hypothesis. To this aim, we tested anatomical consistency of 3 ankle joint models with increasing level of personalization, comparing them also within personalized musculoskeletal models. We build personalized musculoskeletal models starting from an MRI representation of the subject for 17 monolateral legs, and then we model the ankle with 3 different models: a scale generic, one fitting morphological anatomy of the ankle, and another one with floating axis maximizing joint congruence through the ankle motion. Musculoskeletal outputs for the 3 ankle joint model was quite similar if we used standard simulation without considering ankle internal forces, as we can see, with scale generic being the only one slightly different from the others. However, the 3 joint model behaved quite differently, both in terms of ligament elongation, as you can see in the first row, and in terms of cartilage compenetration, as we see in the second row. In some cases, reaching considerably non-physiological value both of elongation and compenetration. We thus decided to compute the forces associated with ligament elongation and cartilage compenetration and insert them within musculoskeletal simulation. And here we may now observe the impact of the joint internal forces, which was normally neglected from standard simulation of musculoskeletal model. Now the 3 models differ quite consistently. The scale generic joint performed very badly in this case, and the morphological fitting start differing from the maximum congruence model, particularly at the ankle contact force. To better understand the impact of anatomical inconsistency, we may compare the maximum differences between musculoskeletal output with and without considering joint internal forces. And in theory, these differences should be 0, but clearly they are not, and in general they are higher the lower is the personalization level of the model. To conclude, we believe that anatomical consistency provides a solid method to compare the credibility of different joint models, growing with the personalization level. It's important to stress that, unfortunately, musculoskeletal models are intrinsically insensitive to anatomical inconsistency, which thus should be verified prior to applied musculoskeletal model, particularly when joint reaction analysis is performed.